Welcome to this video lesson. Today we'll be talking about intersection of lines and planes. Some of the prior knowledge for this video include plane introduction video and lines in 3 dimensions. When we look at space, there are 3 possible relationships between a line and a plane. One of them is the two intersecting, one of them is for them to be parallel to each other and never intersect, and one of them is for the line to be right on top of the plane, and that's when they are coincident. When the two are intersecting, you will find a distinct value for the perimeter t, where x, y, and z values are the same for both the plane and the line. Here's an example. We got plane pi 1 and line 1. To figure out the relationship, we are going to use the parametric equation and plug in the x, y, and z value into the Cartesian form of the plane. So in this case, 2 times, instead of x, we're going to use 1 plus 2t. Instead of y, we're going to use t. And instead of z, we're going to use negative 3t. Then we are going to expand. So we're going to have 2 plus 4t plus t plus 3t minus 18 is equal to 0. We're going to collect our like terms and isolate for t. We're going to get 8t is equal to 16 and t is equal to 2 when we divide by 8. Since our t value is a distinct value, which is a real number not equal to 0, then the line and the plane are intersecting. To figure out the point of intersection, we are going to plug in the t value into the parametric equation of the line. So x is equal to 1 plus 2 times 2, y is equal to 2, and z is equal to negative 3 times 2, giving us the coordinates of the point of intersection as 5, 2, and negative 6. When the lines are parallel, when we solve for the t value, we will get 0t is equal to k, where k is a real value. So let's look at an example for this. We got our plane pi 2 and line 2 equations here. We're going to use the exact same procedure as we did last time. We're going to plug in the x, y, and z expressions from the parametric equation of the line into the Cartesian form of the plane. And then we are going to expand and simplify. And in this case, we will get 0t is equal to 16. And in this case, if we want to find the value of t, we have to divide both sides by 0, and that value does not exist. And since t cannot be solved, then that means there is no solution, there is no intersection, and therefore the line and the plane are parallel. The line and the plane can also lie on top of each other. In this case, they would be coincident, and that would mean that 0t will equal to 0, meaning that we will have infinite number of solutions. Let's take a look at an example for this particular case. So we got pi 3 and line 3 as our plane and the line, and we're going to use the exact same procedure. We're going to replace x, y, z with the x, y, and z expressions from the parametric equation of the line, and then we're going to expand and simplify. Once we do this, we are going to get 0t is equal to 0, and this means that if we plug in any t values, 0, for example, t is equal to 1, 0 times 1 is 0, 0 times 2 is 0, so t can take any value, and that means that there's infinite number of solutions, and if there's infinite number of solutions, that means the line and the plane are coincident, they're on top of each other, and they share infinite number of points. The summary of the concepts of this video is fast forwarded here, so if you want to pause the video and write down any information, please feel free to do so. And now we're going to look at another example. This is an example which is slightly different than what we have been doing so far. So we want to determine the value of k, so k will be an unknown value for which the line and the plane that are given intersect, or when they're parallel, or when they're coincident. So we need to find that k value for which they intersect, they're parallel or coincident. The equation of the line here is given in Cartesian form, but it's a little bit nicer when it's written in parametric form. So here we will change it to parametric form first. We're going to keep the Cartesian form of the plane as is, and then we're going to use the x, y, and z values from the parametric equation and plug them into the Cartesian form of the plane. Note that the k value here is unknown, and that's okay. It doesn't need to have a value yet. We need to find its value a little bit later on. So we're going to expand and simplify this. We're going to put all the t's together, anything that has the like term t, and the k is going to be separated there, and we'll end up getting 0t is equal to 2 minus k as our final simplified form. Since 0t is equal to 2 minus k, the lines cannot intersect, because if for them to intersect, the coefficient of t has to be something other than 0. So in this case, they will either be parallel or coincident, and it will be impossible to have a k value for which they will intersect. For part B, for the lines to be parallel, that means that 0t should equal to any value but 0. So we're going to just do that. So 0t cannot equal to 0, and that means 2 minus k cannot equal to 0. If we solve for k here, we will get that k cannot equal to 2, but k can be any other real value. Finally, for the last part of the question, for them to be coincident, that means that 0t should equal to 0. So in this case, 0t is 2 minus k, so 2 minus k needs to equal to 0, and therefore k needs to equal to 2 for the line and the plane to be coincident or have infinite number of solutions. I have prepared 3 questions for you folks to try out on your own, and I will try to post a solution to these as soon as I can on a separate video. I hope that this video was helpful in giving you an idea about intersection of lines and planes and the 3 different possible situations for them. Thank you for watching.